So you've heard me hint a couple of times that there's a relationship between delta G and the equilibrium constant K. And there is. And we're about to see what that relationship looks like. It requires us to recognize a couple of things that occur at equilibrium. So at equilibrium, when we allow the reaction just to run away with itself and go as far as it wants to, at equilibrium, when there's no net change in concentrations, that means there must be no free energy involved, because if free energy is negative, it's going to push toward the products. If free energy is positive, it's going to pull back toward the reactants. So at equilibrium, delta G is 0. So there's no free energy available. From our equilibrium chapter, at equilibrium, Q equals K. Because if Q is not larger or smaller than K, it must equal K. So at equilibrium, those two things hold. When these two things are true, which is at equilibrium, the equation we've seen just a bit ago that relates delta G and Q at a set of conditions, when Q equals K, we get something interesting out of that. So our delta G equals delta G0 plus RT times natural log of Q. We sub in these two things. 0 equals delta G0 plus RT times the natural log of K. Now we have a single equation that relates the value of K to the standard free energy. And we rearrange this. There's a couple of different ways that we see this. The first way we see it is when we want to calculate delta G. Getting delta G by itself, bring the other term to the other side. Delta G0 is minus RT times the natural log of K. So if you know the value of K, that's your route to calculating delta G at standard conditions. The other one is if we know delta G and we want to calculate K. This one you see in textbooks 2 or 3, sometimes even 4 different ways to format this one. So we rearrange this and we end up with natural log of K equals delta G over RT, and we have to carry the sign over also. So that's one way we'll see this. We'll also see it as K equals E raised to the power of minus delta G over RT. And we'll also see this, depending on who your textbook writer is or your algebra teacher was, inverse natural log, ln to the minus 1, inverse natural log of minus delta G over RT. So it's based on whether you know G or K. I guess you could also do a temperature one in there too if you wanted. But temperature's going to be 298 all the time because these are standard conditions, delta G0. So we're going to work a problem where we do some manipulation there. So we come across this reaction. That it has delta G0, a value of minus 14.2 kilojoules per mole. And we're going to calculate the value of Kc if we know what that one is. Now we should expect a delta G having a minus 14.2 value. That's a spontaneous one. We should expect a Kc larger than 0. Sorry, larger than 1. So we plug this guy in. We're going to use the bottom relationship here. So K equals E to the power of minus 14200 joules per mole Kelvin. Let me pause there a second and tell you what I did. Okay. From the equation, it's a minus delta G, and delta G is negative, so I have to have both of them there. I also changed this to joules per mole Kelvin so that it matches my units on R. Over 8.314 joules per mole Kelvin, and 298 K. So we're going to type this through. I'm going to do this in 2 stages. I'm going to get the intermediate stage first. K equals e to the power of. We're going to do the parentheses part first, because this can be a little bit tricky conceptually. The negative signs are going to flip. So it's just 14,200. Negative signs cancel each other out. Divided by 8.314. Divided by 298 equals 5.73. So K is equal to E raised to the power of 5.73. So with that number still on your screen, it's just second function, natural log, 308.4. Again, no units on K. Always stop and make sure your answer makes sense. We had a delta G value that was negative. That means K should be larger than 1. And it was. Okay?